exceptional resistance to steam corrosion. Professor Ramesh Singh is a prolific researcher and has published more than 300 research articles in various ISI or Web of Science or Scopus listed publications. He has also filed numerous patents for his inventions and received many accolades as a distinguished scholar. He was the recipient of the prestigious IEM Young Engineer Award and has won more than as a top 12 Malaysia Engineer Stars by the Institution of Engineers Malaysia for his notable contribution in the field of engineering education and advancement in ceramics engineering in this country. More recently, Professor Ramesh Singh was the recipient of the prestigious Science and Technology Award 2014, awarded by the Malaysia Torre Science Foundation in recognition, again for his outstanding achievements in the field of ceramics, science and engineering, advanced machining and material processing, and development of nanostructured materials in Malaysia. Professor Ramesh Singh is currently a Chartered Engineer with the Engineering Council UK, a Chartered Professional Engineer with Engineers Australia, a Professional Engineer with the Board of Engineers Malaysia, and Fellow of 5 prominent professional societies. He is on the International Editorial Board of Ceramics International, a Q1 Web of Science Elsevier published journal, the Editor-in-Chief of the Journal of Mechanical and Materials Engineering, a Scopus listed publication, and an editorial board member of the Journal of Institute of Materials Malaysia and Journal of Industrial Technology. Besides research excellence, Professor Ramesh Singh is also a distinguished professor in mechanical and materials engineering in the country. Currently, he serves in numerous capacities as external assessor, professional mentor, resource person, external examiner, advisor, and engineering accreditation panel. He holds a joint appointment as an associate director with the Engineering Accreditation Department, Board of Engineers Malaysia, for his notable contribution in upholding the standards and quality of engineering education in Malaysia. I therefore have the singular pleasure of inviting Professor Ramesh Singh to deliver his inaugural lecture entitled Progress in Low Temperature Degradation of Zirconia Ceramics. Professor Ramesh Singh.
Thank you, Professor Awang. Good morning, distinguished guests, fellow colleagues, friends, researchers. It's a great pleasure for me to stand here today to deliver this inaugural lecture entitled Progress in Low Temperature Degradation of Zirconia Ceramic. Before I start my lecture, normally I would give a lecture for 2 hours, but I was reminded that I have about 45 minutes today. So I'll try to make it as short as possible. But before I start the lecture, I just want to tell you a small little story. If you ask my daughter, what do your father do? And she would say, he's an expert in toilet bowl. And sometimes I will correct her and say, no, I'm actually an expert in using the toilet bowl. Okay, that's what normally people associate ceramics with. As we know, ceramics are used for low-end application as toiletries, as kitchenwares, and so on. So is there another view about ceramics? And the answer is yes. And today I will present to you an exciting area where engineering ceramics, known as zirconia, is being used. To the ladies, probably zirconia known to be their best friend as jewelry. But to engineers, it has more application because of its properties. Okay, what I've done is, because it's difficult to present a fully technical talk, because there's audience from all various backgrounds, so I've basically structured my presentation to cover the following topics. I'll give a brief overview of what zirconia ceramics is, and I touch about yttriotetragonal zirconia polycrystal, the application of zirconia, low temperature degradation, that's what the main topic about in this lecture, and what are the factors that controls the low temperature degradation, and what are the methods that has been used to suppress this LTD phenomenon. And then I'll talk about my work, what I've done over the past 20 years in providing solution to the industry pertaining to this material. And then I will give a short concluding remark. Okay, if those who are familiar with zirconia, zirconia can exist in three crystalline structures. And they are the monoclinic, which exists at room temperature, and they are normally in a loose particle form or in powdery form. And when this material is heated up to about 1100, it transforms from monoclinic to tetragonal. And as we increase the temperature, it goes from tetragonal to cubic form. Now, what is important to see in this structure, in order to appreciate why LTD takes place, is that if you look at the dimension, the axis dimension A and C, and the angles, they are not the same. Now, as transformation proceeds from monoclinic to cubic, there is a volume shrinkage, and there is a structural change from powdery loose particle into a solid structure. And normally the tetragonal are fine structure, as shown in the SEM micrograph at the bottom there. And as it proceeds to cubic, the structure enlarge. And cubic normally known to have very large grain structure. And upon cooling from 2300 degrees centigrade down to room temperature, a reverse phase transformation takes place, where cubic will transform to tetragonal and then back to monoclinic. So what's the problem with that? On heating, there is a volume shrinkage. On cooling, there is a volume expansion. Now, this in turn creates stress in the structure. As I shown earlier, you know that the dimensions are different, the angles are different. And therefore, pure zirconia has very low appeal as engineering ceramic due to the reverse transformation. And normally, the sintered body exhibits severe cracking because of the volume expansion. Now, in order to overcome this problem, the interest in zirconia for engineering application lies in the solid structure form. So it's either in the tetragonal structure or it should be in the cubic form. Now, in order to stabilize the tetragonal structure or the cubic structure to room temperature, it is important to stabilize the zirconia material. Now, various stabilizers have been considered, such as magnesium oxide, calcium oxide, and yttrium oxide. Now, what happens when these stabilizers are added? It actually changes the chemical free energy. I will not go into the science behind the transformation, but basically it changed the chemical free energy, which prevents the tetragonal to monoclinic transformation on cooling. And thus, it is possible to retain at least the tetragonal form or the cubic form at room temperature. And this final structure would depend on the type of stabilizers being used, the particle size, and the sintering condition. Sintering is a term that is used in the ceramic field, whereby consolidation of the particles take place. It's something like cooking, but because it is done at high temperature, so the scientific term is called sintering. Now, of particular interest, the addition of 2.5 to 3 mole% yttrium oxide as stabilizer, resulting in the retention of solid tetragonal structure at room temperature, and that's where the maximum or enhanced mechanical properties are retained. And this material subsequently known as yttrium tetragonal zirconia polycrystal, or Y-TZP. Okay, when we look at the Y-TZP material, it has exceptional strength and toughness, mainly because of its tetragonal structure. And it has been used in many applications, in biomedical fields, in dentistry, in mechanical engineering fields. Now, why the tetragonal structure is important to zirconia? Zirconia exhibit a very peculiar behavior known as transformation toughening. Now, this is a self-healing mechanism. So what happens is that when the material is in the tetragonal structure, it responds to stress. When there's an external applied stress, like in the form of a crack trying to propagate through the structure, the material tends to absorb this stress, okay, and result in transformation. So how strong is Y-TZP? Okay, if we look at this figure, this table, what I've done is I put alongside Y-TZP, properties of Y-TZP with steel. Now, if you look at the tensile strength of zirconia, it is very close to cast iron, or rather mnemonic 90 steel, or mild steel. Now, what is important is look at the Young's modulus, the E. Now, it is almost similar to mild steel, that is in the 200 gigapascal range. Okay, as a result, ceramic zirconia is sometimes known as ceramic steel. Okay, as I mentioned just now about toughening mechanism, so what happens is that when there is a crack trying to propagate through the material, the surrounding tetragonal structure will absorb the stress, and energy needs to be used to do work. So as a result, phase transformation takes place in the vicinity of the propagating crack. And as this progresses, as more stress is induced by external loading, forcing the crack through the material, you have transformation taking place at the tip of the crack into the monoclinic form. Now, because the bulk of the material is still in tetragonal, as a result of that, there is a back stress imposed onto the wake of the crack. And this results in closure of the crack. And these are experimental evidence which I have obtained through my research to show the effect of transformation toughening. What you have seen there is a viscous indentation made on the material. And the load applied for this particular ceramic is about 100 kilogram force. Now, what you don't see is the crack emanating from the diagonals of the indent. But instead, what do you see is a surface uplift phenomenon. So this shows that transformation toughening has taken place, and the material has nowhere to move except upwards, the free surface. Okay, what are the applications of zirconia? Most famous is for grinding, as a grinding media, which is used to grind metals, powders. It is used in the paint industry and so on. Various sleeves and bearings made out of zirconia because of its high inertness to chemical and also good insulation properties and high mechanical strength. So it helps itself as a good material for sleeves, bearings. For palms, face seals, polishing supports, hip joint femoral heads from zirconia. This is for hip implant. This is something that I've made over the years, zirconia knives, surgical blades. You can find now cheaply the available zirconia knives in the marketplace made out of Y-TZP. I've made shaving blades for customers and also surgical blades. I've also made cutting tools for the semiconductor industry using zirconia ceramics. It is not easy to form zirconia. Being ceramics, it is brittle, and we can't use the normal metallic processes or powder metallurgy technique in forming zirconia shapes. And the other application is, of course, as zirconia dental implant. Now, what I've shown you is all still images. Now, in order to appreciate this application of zirconia, what I'm going to show you next is a video. So maybe I should give you a head start what the video is about. It's about a procedure for dental implant. Now, what you will see in this video is the use of zirconia. From the tool, the drill bits, right up to the implant itself. Hold on, that's okay, so basically, a rotten tooth is being pulled out, and now the procedure is to replace that with a dental implant. And this dental implant is made out of zirconia. Okay, this is a pilot tool made out of zirconia. It is used to mark the position where the implant will be placed. And a pilot hole, if you look at the drill bit, it is basically made out of zirconia material. So this is to ensure that the whole drill is in a proper position. This is to widen up the hole. Again, the tool is made out of zirconia. The size is too small, so we need to widen it further. And a slightly bigger hole, 3.75 mm. The implant size is 5 mm. This is to prepare the tulip so that tapping can proceed later in order to make the trading. Again, it is zirconia tool. And now the zirconia implant is basically screwed into position. Okay, and a final, just a hand tight. And then the preparation of the area, the abutment, it is basically chamfered, and then the zirconia tooth is being put in place, or gum in place. And there you go, good as new. So all zirconia, from the tooling right up to the final tooth. So it's very important to preserve nature. Okay, that video is basically to highlight the application of zirconia in at least one area of engineering. In this case, of course, is the dental. Obviously, I have other videos which shows hip replacement, but I think that is a bit too graphical, yes. Okay, so let's move on into what low temperature degradation is all about. Now, what so far I've shown you is the good side about the material, the understanding about its properties, about its structure, about the transformation toughening. So transformation toughening depends on the retention of tetragonal structure, and upon application of external stress, it transforms, and this creates a back stress and enhanced toughness. Okay, this material suffers from low temperature degradation. So what is low temperature degradation? Sometimes it is known as aging. Now, what have been found over the years is that degradation proceeds most rapidly at a certain temperature range between 150 degrees centigrade to 300 degrees centigrade. And the degree of deterioration is dependent on the aging time, how long it has been exposed, the environment, and also the presence of pressure, hydrostatic pressure. So that's where the steam comes in, because steam, you have water and you have pressure. Now, transformation normally starts at the surface, and it progresses internally over time. Now, water or hydroxyl can be present in the form of liquid, vapor, or in other solutions, such as in acid, is the catalyst of the phase transformation. So water has been identified as the culprit. Okay, but having water alone, it will not work. It has to have temperature. And it becomes worse when there's hydrostatic pressure. So two tactics employed in suppressing degradation is increasing the stabilizer content, that is the yttrium oxide content in the structure. But this has a bad effect because it overstabilizes the tetragonal structure into cubic form, and it loses transformation toughening. And the other strategy is to decrease the grain size of the sintered material. Okay, so when transformation takes place, when LTD or low temperature degradation takes place, this is normally accompanied by microcracking because of the volume expansion as tetragonal transform into monoclinic. And the diagram there shows the samples that has been prepared before and after aging. This material has been exposed to superheated steam for 24 hours. So it breaks or crumbles into powder. And if we look closely into the structure, it developed massive microcracking. So how serious is LTD? Now, zirconia being used in the medical field, especially for femoral heads for hip replacement. Sometime in 1997, there is a statement released by FDA, US, warning surgeons on the steam sterilization of zirconia femoral heads used for hip prosthesis. So for those who are not familiar, I could show you a video on this procedure as well, but I think we'll skip for the next lecture that I'll do. So in this case, the head is made out of basically zirconia, and the cup, as you can see in the acid tabular cup, the stem is made out of stainless steel or titanium. And this is basically placed, the titanium stem is basically put in the femur, and the other part goes into the hip bone. Okay, so what happens is that the warning issued by FDA is that when the zirconia head, when it is exposed to steam environment, it may lead to phase transformation. So therefore, FDA has cautioned surgeons not to sterilize the zirconia head in steam environment. And this has an effect on the manufacturers because fracture of the head has been observed after 13 to 32 months of implantation. And close examination done on these fracture femoral heads reveal high monoclinic content. So phase transformation has taken place at body temperature, so over a period of 13 to 32 months. So what are the factors governing LTD? So these are the main factors: the grain size, the tetragonal grain size, the stabilizer content, the temperature, the distribution of the stabilizer, and the test temperature. So I quickly run through classical example of findings of other people's work to demonstrate what are the factors or how these factors actually controls degradation. LTD increases with tetragonal grain size. So as the grain size increases, so do the phase transformation. What the diagram shows there, if you look at the blue dots, the grain size is 1.6 micron. The red dots, the bottom graph, it is at 0.2 micron. Phase transformation takes place, but at a very minimum level. So there is an effect as the tetragonal grain size increases, so do phase transformation. There is a critical grain size being postulated that actually controls the phase transformation, and this critical grain size depends on the stabilizer content. That red line shows you the boundary. For example, if we take 3 microns, the limit is, the critical grain size limit is 0.3 microns. So if the grain size exceeds this limit, it goes into an unstabilized region, and upon exposure to steam environment, it actually transforms. In terms of stabilizer content, that is the yttria that is added to stabilize the high temperature crystalline structure that is the tetragonal form into to room temperature, has an effect as well. Now, increasing the stabilizer content from 2 mole% to 3 or 4 mole% obviously has an effect in suppressing or reducing the phase transformation, as the graph shows there. In terms of temperature, temperature has an effect as well. In the case of the femoral head, the earlier example, it is done at body temperature. So temperature is low, but over a certain duration, a long period, it transforms. Now, as temperature increases, so do the rate of phase transformation. And what that graph shows you, if you look at the red curve, maximum phase transformation takes place at about 200 to 300 degrees centigrade. And during this period, there is a maximum drop in the mechanical properties as well. Aging at higher temperature has lower effect, or aging at lower temperature has lower effect as well, as shown by the red curve. At 100 degrees, the monoclinic phase content is low. So there's a temperature dependence in terms of controlling the LTD as well. Now, there is a dispute about stabilizer distribution, how the yttrium, the yttria oxide is being distributed throughout the material, the starting material in the powder form. So there is 2 arguments. One is by coating yttria on the surface of the particle, and the other argument is to co-precipitate the stabilizer into the structure. So what that diagram shows is the 2 effects. The first one, yttria is being added onto the surface. The second one, it is basically infused with the monoclinic particle. And this is to support the theory which state that in order to have a narrow grain size or fine grain size, you must have homogeneous distribution of yttrium in the starting material, as the diagram shows you for the curve 1. And the diagram on the right, the extreme right, shows you the distribution of grain size. So in order to have a stable structure, that's what the theory postulated. Okay, that's what the theory says. If you have an inhomogeneous yttria distribution, as in curve 2, so wider distribution, because of the inhomogeneous nature of the yttria being distributed in the structure, there is a possibility of the tetragonal structure being unstable, and it will then transform during LTD, or exposure to steam environment. Now again, experimentally it has shown that this is not the case. What the graph shows is the effect of aging or LTD on the bending strength of this material. As you can see that the two Japanese powder, Toso and Daiichi, they are co-precipitated zirconia powders. Now they degrade or they break up within less than 25 hours of exposure in steam environment. Now in the case of coated powder, where the starting material, the yttria, has been coated onto the material, it survived for more than 200 hours. Now the test environment has an effect as well. If it's fully water, then the degradation is rapid. Okay, the LTD responds to hydroxyl, so it is rapid as compared to air. In the same case, when it is being exposed to vacuum, there is a temperature dependence as well in vacuum, where phase transformation still occur. But obviously in water, it is much rapid. So what are the methods being adopted by researchers and engineers in order to suppress LTD? So one of the famous method is to apply pressure-assisted techniques such as hot pressing or hot isostatic pressing to lower the tetragonal grain size. For those who are not familiar with this technique, it is simply a consolidation technique whereby temperature and pressure are applied simultaneously to consolidate the material. So as a result, we are able to consolidate the material at low temperature because it's pressure assisted, and therefore we can suppress grain growth. And so we are able to retain fine tetragonal structure. The other method is to coat the surface of zirconia in order to interrupt the reaction between hydroxyl with ZR. Now this is done by using sophisticated equipment and processes such as chemical vapor deposition, physical vapor deposition, electron beam evaporation, and so on. Now these are expensive techniques. So basically what happens is that we coat the surface with a layer of another material in order to prevent hydroxyl from reacting or coming in contact with the tetragonal structure. The third method obviously is surface modification. And this is done by converting just a micron layer of the tetragonal structure on the surface into the stable cubic form. And this is done by using some post-heat treatment processes at very high temperature and in controlled atmosphere. Now the cubic structure is known to be stable because it has high yttria content. So therefore it will not react to hydroxyl. In the form of tetragonal, the stabilizer content is insufficient to create that boundary to prevent hydroxyl from reacting. But what are the effects by having a cubic structure is that the downfall is that transformation toughening is affected. Because for that to be fully effective, it needs to be in the fully tetragonal form. So by increasing the yttria content 3.8 to 3.8 or to 4 mole %, the tendency is to overstabilize the tetragonal grain. So again, there's too much of stabilizer there. It interrupts in the transformation toughening process. For transformation toughening to take place, the tetragonal grain has to be in the metastable form. It cannot be in the stable form. So you should start with, you should keep the 2.5 to 3 mole % yttria. So basically, the development of LTD zirconia in the case of my work started in 1994. Now this is a research done with Dioxide UK. Basically what we did was to use the plasma technology used to make titanium dioxide in order to coat yttrium onto zirconia particle. Now the objective is to improve the mechanical properties and to basically reduce LTD or suppress LTD by the use of sintering additives. And what we found through the research is that we are able to enhance the mechanical properties. So exceptional high toughness obtained with copper oxide doped. If you look at this diagram, the values there shows that values in excess of 20 megapascal meter the power half is possible with copper dope zirconia. Normally, zirconia would exhibit values in the range of 5 to 8 megapascal meter power half. And later, through further research, we found the reasoning for this enhancement in the toughness and in the strength. The plasma process actually coat yttria onto the surface of the monoclinic zirconia. And when sintering proceeds, it creates a coring effect. What the diagram shows you there is that you start with a powder, a coated powder, sinter at about 1100, 1200, tetragonal structure form, but the yttria stabilizer concentrate more on the outer shell than the inner because the diffusion of yttria in the particle is slow. So it is temperature dependent. And of course, further increase in temperature causes more diffusion of yttrium, the stabilizer, into the structure, and therefore it also induces grain growth. Now, through transmission electron microscope, we found evidence of a coring effect, as I mentioned, a tetragonal monoclinic core structure, where at low temperature, the core of the tetragonal grain is still in the monoclinic form, but the shell is in the tetragonal shell. The core is monoclinic, the shell is in the tetragonal structure. Now, this creates a metastable structure because the boundary between the tetragonal structure, the tetragonal shell to the core, there is a reducing concentration of yttrium oxide. Okay, I did not show the detail here, then I'll be going into too technical. But what we found is that there is a high concentration of yttria at the boundary and very low concentration of yttria at the center of the grain. So that creates a metastable grain, which will respond immediately to propagating cracks. And that enhances the toughness. Now, this effect we don't find in co-precipitated powder, because co-precipitated powder, the yttrium oxide has been distributed homogeneously within the structure. So therefore, it stabilizes the structure, and the yttria distribution from the shell to the middle is almost constant. In terms of LTD, low temperature degradation, there is some improvement. As the graph shows, with the copper oxide doping, we managed to suppress the phase transformation, but not to prevent it. It still happened, but the amount of transformation is lessened. So we obtained with 0.5% copper oxide doping, the phase transformation, the monoclinic phase is about 30% as compared to the undoped. So is that good enough? That's really not good enough. Because what we want to do is to develop a fully resistant, where it will not transform under exposure to steam environment. So what are the problems associated with most of the solution that I've just presented? Now, they have their uniqueness. They use expensive equipment, expensive chemicals, high technology, and as a result, the end product is expensive. So therefore, there is a need for a simple, reliable, reproducible method to produce tetragonal zirconia that exhibit excellent sinterability at low sintering temperature using pressureless sintering process. All right, so we don't want to use expensive equipment. We want to keep the temperature low, and we don't want to use expensive chemicals. And so we go back to the drawing board. So the focus is to develop a completely LTD-resistant zirconia without sacrificing mechanical properties, because this material is used for mechanical application, so we need to preserve mechanical properties. At the same time, we want to enhance or completely prevent low temperature degradation. And of course, to keep the processing cost to a minimum. So over the years, many techniques were looked at, basically focusing on microstructural re-engineering through the use of transition metal oxide to modify processing techniques so that we can produce nano-range particles, to adopt pressureless sintering method. That has always been the objective, is not to use expensive equipment. And this has been done through FYP, master's research and PhD research over the years. So what are the significant findings? All right, so what we have found, my group have found that the use of manganese oxide is most effective. Small addition of MnO2 in the zirconia aided sintering at relative low temperature, so that's one of the objectives. We are able to lower the sintering temperature without inducing grain growth. And the said body is able to even densify at even lower temperature and using very short holding time. And we managed to achieve 12 minutes holding time. Now, this scenario normally could only exist with pressure-assisted technique like hot pressing or hot isostatic pressing. So you need pressure to be present during the sintering to achieve high density at very low temperature and at very short time. So these are some of the results. So what I want to highlight is I picked two compositions, the 0.5 weight percent and 1 weight percent manganese oxide doped. Now, if you look at the relative density, this is sintered at 1150 for 2 hours. If you look at the density, we are able to achieve above 95% with manganese dope. In terms of the modulus, up to 180 gigapascal as compared to the undoped. In terms of hardness, the undoped is about 2, and the manganese dope is 11 gigapascal, 12 gigapascal. This is another one at low time, so we increase the temperature slightly to 1300. We are able to reduce the holding time during sintering. So if you look at 12 minutes, here comparison is made between the undoped and 1 weight percent. If you look at the density, 89 to 97%. The Young's modulus from 155 to 200 gigapascal. Okay, and the viscous hardness from 8 to 13 gigapascal. So there is a significant improvement in the properties at low temperature and at low holding time. Now, in terms of LTD, low temperature degradation, this material outperformed commercial zirconia powders and also the undoped material. If we look at the monoclinic content after 1,000 hours of exposure in a steam environment, at 180 degrees, at 10 bar pressure, there is no phase transformation at all. So 0, so it is still 100% tetragonal structure. So these are some other findings that we observe through the research, which shed some light into the mechanism, what actually controls the LTD. Now we found various diagrams which shows nucleation site where we think that monoclinic actually starts. So it's like a wound on the structure, on the surface of the structure, where water penetrates that area, creates stress, causes transformation. And this structure shows you the nucleation site. So this is another diagram to support that theory. We see a nucleation site on the surface and it propagates. AFM atomic force microscope also support the findings. We see crater formation around this area where the nucleation of monoclinic takes place. So based on this, a mechanism has been proposed. I will not go in detail on the mechanism. It's a 3-step mechanism. The first one, hydroxyl, attacks the surface, mainly at grain boundary. We have evidence to show that it is the grain boundary that the hydroxyl actually attack, and it creates monoclinic nucleation. And as the monoclinic grows, it creates microcrack. And in the step 2, there is a growth of the monoclinic particle within the tetragonal structure, and this is accompanied by microcracking and further ingression of hydroxyl into the structure. And this causes neighboring grain to start to transform. So there is an autocatalytic behavior that causes transformation to proceed deep into the material. With further cracking, microcracking formation, more ingression of hydroxyl into the structure, more transformation takes place. And eventually, the earlier structure that has been transformed, it will be expelled upwards. And that's where we see crater formation. Okay, as just now, Prof. Awang highlighted my recent work with a boiler manufacturer in the UK. Sometime last year, I was contacted by Spirax Sarco. The chief scientist has read some of my papers, and they contacted me because they don't believe that zirconia can actually withstand steam environment, because they have tested on many commercial zirconia in their plant, and it all failed. And so I was asked to share my secret with them on how I developed this LTD completely resistant material. And so I told them that why not they try out some samples in their plant, in the actual condition, because all my tests is done in the lab. And it is at 180 degrees at 10 bar pressure. And so I made cylindrical samples, commercial, the white one, and my formulation, the brown or the black or the darker color one. And this was sent to UK, and they made a setup. They have a boiler running, and they have a continuous flowing of steam. They tap out from this boiler at 60 bar, 274 degrees centigrade. And they pass through this mini setup where the samples are placed in that small chamber. And this is the outcome. So commercial zirconia fragmented in less than 30 hours. My one survived 1,000 hours. So basically, that's not the end of the story. They were impressed, and there were a lot of discussion went on. And what they actually want is that they are coming up with their new line of boilers with a new design. I'm not able to show the full design here because of a patent issue and so on. But this schematic diagram shows where they want the valve, the ceramic valve, to be seated. And they want it to be in a circular form. And the diameter, the option they have given me is that they prefer option 1, where the diameter has to be precisely 12.7 millimeter. And I told them that it's not possible for me to do it because I'm not a manufacturer. I'm a university professor, and I have a small lab. And I told them that they have to give me more options. So they came up with option 2, option 3, option 4, and option 5. All right, so it is not easy to make ceramic or zirconia in that sense into any form we like. There is a limitation. As you know, ceramic is brittle. It is not like metal where you can make a block and then you can just subject it to turning operation to shape it into any dimension you like. So with ceramic, we have to use a near net shaping format where we need to press it into shape. And therefore, after trying out designing the dies, making some samples, and looking at how we could narrow down our final mold to the dimension requires, we managed to actually produce option 5. So this is about 13 mm, not precisely 12.7, but it is slightly above. It's about 13 mm. It's a conical valve, and now the valve is in the UK, and it's being tested. Okay, so that brings me to the end of my presentation. So basically, what I've shown in this talk, what I've shared with all of you, is the development of a LTD-resistant zirconia using pressureless sintering method. And in this technique, the material that I produce in the lab can be sintered at very low temperature using the pressureless sintering method, so I'm able to keep the cost low. Now, at the same time, I maintain or enhance the mechanical properties, and I basically suppress or completely prevent low temperature degradation. So what the future lies for this material? So basically, the future of zirconia would depend on the ingenuity of the researchers to tailor the ceramics to suppress LTD. So if you work with zirconia, it will always degrade in steam environment. So the challenge would be to integrate only processes that can deliver zirconia with tailored microstructure and properties such that iterative improvements are possible. Because with ceramics, you can't subjected to annealing treatment or treatment that is common to metallic material. So here the challenge would be to have a zirconia material that we are able to use other processes thereof after we manufacture the article to change its properties or to tailor its properties to a particular application. Okay, I would like to acknowledge the top management of Universiti Malaya, the Faculty of Engineering for the funding, the infrastructure support to facilitate my research, Mohi and Mosti for financial support over the past 20 years, my past and current research student for being supportive. You know I'm a difficult supervisor to work with. I have very high standards because I always believe that there's no shortcuts to success. And last but not least, my family and friends and colleagues who have inspired me in this exciting, challenging, and enjoyable journey to be where I am today. Thank you very much.
Thank you very much, Prof. Ramesh Singh. You know, I don't often get the opportunity to chair inaugural lectures. I probably chaired around 10 of them or so in the past few years that I've been Deputy Vice Chancellor. And each inaugural lecture that I chair, I learn something new. One of the things that struck me today, and among other things, is, and I'm sure you share with this, when you come back to Malaysia from a trip from abroad and you step into KLIA, which is the entry point for most people into Malaysia, you experience how hot and humid this country is. The humidity of our country causes problems as well as contributes to the economic prosperity of this country. Today I've learned that the humidity of Malaysia can be a problem for zirconia. Low temperature degradation of zirconia is one of the issues. And zirconia being a ceramic which is, I believe, widely used, not only in the industry, as you can see, but also in dental applications and medical applications. I hope that the inaugural lecture by Prof. Ramesh Singh today does not turn you off from going to see the dental surgeon. As you can see, some of dental colleagues here today. I've also learned something which is very useful, perhaps not just for me, but also for others in this room. When one publishes high-impact research in high-impact journals, there is always that possibility that the work of colleagues like yourself, Prof. Ramesh, will lead to work with industry, which is what I would say will be the highest recognition of somebody's contribution to new knowledge generated from research. I believe that Prof. Ramesh Singh, through his work, through his research, has demonstrated clearly this link between academia and industry. For your information, your name did crop up in conversations I've had with colleagues from other universities. And I think the respect and admiration they have for your progress in R&D throughout the years is testimony to the kind of scholarship, of learning and research that we have come to expect from professor in the University of Malaya. With that, I am sure you will agree with me that Prof. Ramesh Singh has delivered an excellent inaugural lecture, and will perhaps join me in congratulating and thanking Prof. Ramesh Singh for his inaugural lecture today. Thank you very much.
Thank you, Professor Dr. Awang Bugiba, for chairing the lecture. I would like to take this opportunity to thank the management of the Faculty of Engineering, International Corporate Relations Office, citizens of University of Malaya, as well as all the guests here for your time. With this, we have reached the end of the lecture. On behalf of the University of Malaya, I would like to apologize if there have been any weaknesses from our side in organizing this event. Refreshment will be served. For guests, visitors, top management's refreshment will be served at Bilik Persidangan. For students and staffs, refreshment will be just outside the lecture hall. Ladies and gentlemen, once again, thank you and have a pleasant day. Thank you.